We want to talk about page 6, beginning on page 6 today of the discrete distribution lecture. So the first thing it talks about is combinations. The number of ways of choosing R objects out of N objects, where order does not matter, is given by N choose R. We've seen this before. N choose R, which is also written N choose R like this. This means N choose R. And the formula, of course, is N factorial over R factorial N minus R factorial. And we know that 0 factorial is defined to be 1. And we had said last time when we learned about this earlier in the semester that N choose R is also equal to N choose N minus R, because both of these would have exactly the same formula, which is that. That's if order is not important. So if I said to you the number of ways to choose 6 people out of 10, you would say 10 choose 6, right? No order. Order is unimportant at that point. This next paragraph talks about permutations, and that is when order is important. So if order were important, then permutations so NPR, the number of ways of choosing R objects out of N objects where order matters, is N factorial over N minus R factorial. So if I say to you, I have 10 people and I want to choose a president and a vice president, then all of a sudden it matters whether the first person picked is here or here, so I care all of a sudden. This would be 10p2, which is 10 factorial over 10 minus 2 factorial, or 10 factorial over 8 factorial, which is just 10 times 9, which is 90. Here, order is important. So we'll mostly be talking about N choose R in this chapter, no NPR. But I wanted to mention this while we were here. So this brings us to the last paragraph of page 6. Binomial distribution. It's an example of a discrete distribution. We talked about discrete distributions last time. Discrete distributions have valid probability mass functions. PMFs. That means something like this: xi, p of xi, where the sum of the probabilities is 1. and every p of xi is greater than or equal to 0. Non-negative probabilities. We talked about this last time, right? So I'm now saying that this binomial distribution that we're going to be talking about today is just a special case of a discrete distribution, so that it will have a valid PMF where the probabilities are non-negative and the sum of the probabilities is 1. So these two conditions will hold, as these two conditions hold for every PMF. Okay, so I'm on the last paragraph of page 6. Consider an experiment in which we toss an unfair coin. Let me take a new page. So it really begins here. Let's call this so I have an unfair coin where the probability of heads is 2/9 and the probability of tails is 7/9. So it's unfair, meaning the probability of heads is not equal to the probability of tails. Each toss is called a trial. Each trial has exactly 2 outcomes, heads or tails. Such a trial with exactly 2 outcomes is called a Bernoulli trial. So a Bernoulli trial has exactly 2 outcomes. And every time I toss this coin, I will have a Bernoulli trial because I have exactly 2 outcomes, heads or tails. In a single Bernoulli trial, P is the probability of success. P is the probability of success. So what do we want to call successes? Maybe heads are successes in our case. So let's call this probability of heads. So in our case, P is 2/9. Probability of heads, because I am letting my heads be successes. And Q is the probability of failure. Probability of tails in this case. So my tails are failures because I assign it that way, 7/9. And Q, of course, is just 1 minus P. Those two add up to 100% at all times. A binomial experiment is one in which there are n independent Bernoulli trials. So every trial has 2 outcomes, meaning every toss has 2 outcomes. And let me toss this coin a few times. So a binomial experiment is made up of n independent Bernoulli trials. So in other words, tossing coin 3 times, let's say. Here n is 3. So if I toss this coin 3 times, this would be a binomial experiment because every toss has heads or ends up in heads or tails. Every toss is a Bernoulli trial, and I have 3 independent Bernoulli trials. What occurs on the second toss is not impacted by what happens on the first toss, so they're independent. Right? Let's consider another binomial experiment. Let's say that you get to the parking lot, the computing center parking lot, and either you park legally or you park illegally. Right? So either you're going to park on the grass illegally or in a handicapped spot, or you're going to pull into a valid spot. And there are 5 people doing this. So that would be a binomial experiment, because each person either pulls into a proper spot or parks illegally. And then there are 5 people doing this. So I have n independent Bernoulli trials. Get it? And that makes up a binomial experiment. Okay, I'm on page 7. Toss a biased coin 3 times. Then each toss is a Bernoulli trial, and the 3 tosses make up a binomial experiment. Find the probability of obtaining exactly 2 heads in 3 tosses, where the probability of heads is 2/9 and the probability of tails is 7/9. So I have set up these already. These are valid. And it's saying there are now n equals 3 trials. Find the probability of 2 heads in 3 tosses. So this R, this 2 is R. R successes. R is the number of successes. And since I want the probability of 2 successes, because heads are a success, my R is 2. So R equals 2 successes. And n equals 3 tosses. So the question is, find the probability of obtaining 2 heads in 3 tosses. So we might begin like this. Probability that the first one is heads is 2/9. Probability that the next one is heads is 2/9. So I have heads and heads, 2 heads, and the last one is tails, 7/9. Am I done? Am I done? What do you think?
No, because you could change the order around and get 2 heads last or on the ends.
Exactly right. So I am not done, because the 2 heads don't necessarily have to be the first 2 tosses. So I'm going to see how many other possible arrangements I have. So of course I could have had tails first and then heads, heads, in which case I would have had 7/9, 2/9, 2/9. Or the tails could have been in the middle, 7/9, and then the heads on either side, like this. So I have 3 possible arrangements where this could occur. So I'm going to say 3 times 2/9 squared times 7/9. Does that make sense? 3 different arrangements. That's where this 3 comes from. And then the probability of heads, which is P, squared, because I have 2 heads, and the probability of tails, which is Q, to the first power, because if I have 2 heads, then the third one is a tail, so there's only 1 tail. So heads probability squared, tails probability to the first power, because I want 2 heads and 1 tail, and then there are 3 arrangements such that this occurs. Get it? What if I were to change this to 5 tosses? What if n were now 5? And I wanted probability of 2 heads in 5 tosses. R is still 2. I want 2 successes. N is now 5. Now what do I do? Can you help me, Vinny?
Yes, first have one heads, and then another heads, so 2 nines.
2 nines squared.
Yes.
Okay, so probability of heads squared. Then what? Right, probability of tails to the third, because if I have 2 heads, then I have 3 tails. And then what's this number?
That would be a combination.
Exactly right. This would not be 5, right? This would be 5, choose 2. Just as this number was 3, choose 2. So look what I'm saying. This coefficient right here is the number of ways of picking the 2 places where the heads will occur out of the 3 places. This number is the number of arrangements such that I have 2 heads in 5 places. So 5 choose 2 turns out to be 10 because it's 5 factorial over 2 factorial, 3 factorial. And this is 5, 4, 3 factorial over 2, 1, 3 factorial. These drop and I get 10. So this is 10. In other words, the heads could be in the first 2 places, or in place 1 and place 3, or in place 1 and place 4, or in place 1 and place 5, or place 2 and place 3, or 2 and 4, or 2 and 5, or 3 and 4, or 3 and 5. You get what I'm saying? So there are 10 such arrangements with 2 heads and 3 tails. Are you with me, guys? Okay, so the general formula is next. In general, and this should be in your notes. In general, let's see, where is it? It's the 3rd paragraph down on page 7. The number of successes, or not, let's say not number, the probability of R successes in n trials is given by n choose R, p to the R, q to the n minus R. The number of different arrangements times the probability of success raised to the number of successes times the probability of failures raised to the number of failures. So this is my formula for the probability of R successes in n trials. Try this problem right now. Yes.
Is the one here in the packet different? Because this one says 5 probability exactly 2 heads and 3 tails and 5 tosses.
Yeah, isn't that what we just did?
Didn't you just do 2 heads?
What does that say?
2 heads and 3 tails.
Isn't 2 heads and 3 tails the same as the probability of 2 heads? Because if it's 2 heads, then don't the rest have to be tails?
Yeah, yeah. Okay.
So it's the same thing,
Okay.
right?
Yeah, I just wanted to make sure.
Okay, try this example. The probability of snow is 0.8. Find the probability that on my 7-day vacation to Colorado, I have 4 days of snow. So because this example is talking about snow, it's asking about snow, that's my success. Because the question is, what's the probability that I have 4 days of snow? So snow is a success. This is R. R is the number of successes. 7-day vacation, N is 7. And P is the probability of snow. Little p is the probability of a success, and since I'm calling snow a success, little p is 0.8. That means Q is 0.2. So this whole question can be written like this. Find the probability of 4 successes. That's written just like that. Probability R equals 4. It's equivalent to just writing probability of 4. It's understood when you say probability of 4 that I'm talking about R equals 4. Meaning find the probability of 4 successes in 7 trials. N is the number of trials. So I'm ready to plug into my formula. My formula is N choose R, P to the R, Q to the N minus R. So 7 choose 4, 0.8 to the 4, 0.2 to the 3. So what I'm saying is I have taken the snow probability, raised it to the 4th power because I want 4 days of snow. No snow probability to the 3rd power because if I have 4 days of snow, then the rest are no snow. And there are 3 remaining. And then these are all the different arrangements where the 4 snow days could fall out of 7. And that's my answer. So I would stick this in my calculator. How do you do 7 choose 4 on the calculator? Of course I can do it by hand if I wanted, but 7 factorial over 4 factorial, 3 factorial. So this would be 7, 6, 5, 4 factorial over 4 factorial, 3, 2, 1. This 3, 2, 1 cancels with the 6. And this 4 factorial cancels with the 4 factorial on the top. So my answer is 35. Does that make sense? How do you do this on the calculator? You first put in the 7, then you go to math, probability, NCR, and then you put in the 4, and then you hit enter. You might have to hit enter here also. So the first number, math, probability, NCR, enter, 4, enter. And this should give you 35. Check it right now. It does?
Yeah.
Super. Question? Okay, so how do you do this whole thing on the calculator? How could I have done this whole problem on the calculator? This part is just 7 choose 4, right? But let's say I wanted the whole thing done. I would go to, let's get my calculator. Here we are. Second distribution, second distribution. And then scroll down till you get to binomial PDF. Which is A on the TI-84 Plus, right? Hit enter. And then it gives you a bracket and it's waiting for the argument for this. And you're going to put in N and P and R. So N is the number of trials, which would be 7. And P would be 0.8 because that was my probability of snow. And R would be 4 because I want 4 days of snow. And you need commas in the middle. So 7, comma, 0.8,
Wait, that's binomial PDF?
comma, 4. I get 0.1147. Do you get that?
Oh, yeah.
Let's just check that against 35 times 0.8 to the 4th times 0.2 to the 3rd. Let's just make sure that it works. 35 times 0.8 raised to the 4 times 0.2 raised to the 3rd power. And I get 0.1147. So it's all good. Get it? Let's say the next question was, so let me label these properly. This is A. And B says, find the probability of at most 4 snow days. At most 4 snow days. At most 4 means R less than or equal to 4. Agree? So I want probability of no snow days, or 1, or 2, or 3, or 4. I would have to do 5 of these products, 5 of these products to get the answer. So this is what I'm trying to say. I would have to do 7 choose 0, 0.8 to the 0, 0.2 to the 7. That's exactly no snow days. Plus 7 choose 1, 0.8 to the 1, 0.2 to the 6 power. Because if I have 1 snow day, then I have 6 of no snow. You follow? And you'd have to keep going like that until the last product, which is gonna be, this is page 4. The last product would be 7 choose 4, 0.8 to the 4, 0.2 to the 3rd power. It's a lot of work. You don't want to do this, you want the calculator to do it for you. The way to do this on the calculator is binomial CDF. Not PDF, but CDF for cumulative. So it's going to do the whole summation for you. Binomial CDF of NPR, where R is the largest one in the group. So N is 7, P is 0.8, and R is 4. This will give you probability R less than or equal to 4 successes, which is what I'm looking for. So it takes the probability of 0 and 1 all the way to 4 and adds it up and gives you the answer. What is the answer? Let's do it. Second distribution, go down to binomial CDF, cumulative. N is 7, comma, 0.8, comma, 4. 0.1480. So of course you access this by second distributions, just like all the other distributions we were doing, right? Get it? What if there was a part C that said, find the probability of at least 4 days of snow? At least 4 days of snow. Now what? What are they asking for?
Greater than or equal to 4.
Yeah. Probability are greater than or equal to 4, which would be probability of 4 or 5 or 6 or 7. Too much work. I'd have to do 4 of the products, right? This is what I'd have to do. 7 choose 4, 0.8 to the 4, 0.2 to the 3, plus 7 choose 5, 0.8 to the 5, 0.2 to the 2, plus 7 choose 6, 0.8 to the 6, 0.2 to the 1, plus 7 choose 7, 0.8 to the 7. I don't bother writing 0.2 to the 0 because anything to the 0 power is 1, right? But it's still too much work. 4 of these is too much work, right? So how about I do 1 minus probability r less than or equal to 3. Because this less than or equal to 3 can be done by the calculator. So let me explain. After all, this is a valid probability mass function, right? It looks like this. xi, p of xi. So if I go away for 7 days, I could have no days of snow, 1 day of snow, 2, 3, 4, 5, 6, or all 7 days of snow. And with each of these is associated a probability. So this is saying probability of 0 days of snow, probability of exactly 1 day of snow, probability of 2 days of snow, dot, 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 probability of 7 days of snow. And I know because this is a valid probability mass function that all these probabilities add up to 100% or 1. So the answer that I'm looking for in part C is this answer. Probability of 4, 5, 6, and 7 added together. Right? It says at least 4 days of snow. So this is my answer. My answer to part C. So what I'm suggesting is that we take the ones that are not included and subtract them from this total of 1, minus these. Probability r less than or equal to 3 includes 0, 1, 2, or 3 successes. Take these away from 1 so that I end up with my answer. 4 or 5 or 6 or 7. Do you see? And the reason why I do that is because the calculator can give me the cumulative total all the way up to 3. So I would do this. 1 minus binomial CDF, cumulative distribution of NPR. So N is 7, P is 0.8, and R is 3. So I'm taking away 0 probability of 0 plus 1 plus 2 plus 3. I'm taking those away from 100%, which will leave me with the probability of 4, 5, 6, and 7 added together. Yeah.
So if there's a case where R was, for example, 3.5, that's not possible because of...
You can't have 3.5 days of snow. It would be an integer value. It would be an integer value. So yeah, you wouldn't be talking about 3.5 days of snow. It would be either one of it would have to be one of these, 0 or 1 or 2 or 3.
And so the calculator understands that it's just discrete value.
Yes. Calculator knows that these are binomial. These have to be integer. Question? So let's see what they're doing on this page right here. I'm on page 7. It's just talking about the assumptions on page 7. It says make sure that, I'm in the last paragraph, there are a fixed number of trials n. Each trial has exactly 2 mutually exclusive outcomes, success or failure. Success probability is p. The outcome of each trial is independent from the others. And the possible values of the binomial random variable are 0 through n. So that's an important point that I just want to bring up again. When you have n trials, you can have anywhere from 0 to n successes. It's very possible to have no successes. So you must include the 0. It's possible to have no days of snow. It's possible to have no heads. It's possible to have no successes. So you would have n plus 1 possibilities here, right? All these n, 7 of them, plus 0. So you would have to find 8 probabilities. Are you with me? Okay, so now page 8. So last time when we were talking about discrete distributions, we had 2 formulas. One was the formula for the mean, E of x, which was also mu, which was also expected value or expectation. These are all different names for the mean, mu. And the formula for these was summation xi, p of xi, I going from 1 to n. And the formula for the variance of x, was given by summation xi minus mu square times p of xi. And then we didn't like that, so we developed a shortcut formula, which was e of x square minus mu square. This was the shortcut formula for the variance. And this was the formula for the mean, the one on the top. Certainly this formula would work for binomial random variables because binomial random variables are discrete. But there is a better short formula that you can go to immediately, and for the mean and the variance, and these are the formulas. So if x is binomial, n comma p, where n is the number of trials and p is the probability of success per trial. If x is binomial np, then do not bother with above formulas. I should say the general formula. General formulas. Don't bother with these. Go straight to the fact that mu for a binomial random variable equals n times p. And variance for a binomial random variable equals n times p times q. So you don't have to bother with all this stuff, which took a long time to do last time. These will immediately give you the mean and the variance for a binomial random variable. So you might be saying, well, where does this formula come from? Let's consider the mean and the variance for a Bernoulli trial, for one Bernoulli variable, right? So consider, maybe I go to another page so that we have room. Where do these come from? So consider a Bernoulli trial where success is assigned a 1 and failure is assigned a 0. Could I not write this variable like this? Success with probability p and failure with probability q, which is equal to 1 minus p. Let me find the mean the old-fashioned way of this variable. So couldn't I say e of x equals summation xi p of xi? That's the formula for finding the mean, right? So I'm going to go this times this plus this times that. So this would be 1 times p plus 0 times 1 minus p. And of course this does not contribute anything. So my expected value is just p. And how about the variance of this Bernoulli random variable? After all, variance of x is equal to e of x squared minus mu squared. This, of course, is mu. That's my formula for variance of any discrete random variable, right? So let's find e of x squared. E of x squared would be summation xi squared p of xi. So square the 1 and times by p. 1 squared times p plus 0 squared times 1 minus p. Of course, this drops. And again, for e of x squared, I still get p. So when I go to plug that into the variance formula, I get variance of x equals e of x squared, which is p, minus mu squared. Mu is also p, so p squared, because this mu got squared, right? Are you with me? So this is equal to p parentheses 1 minus p. I factored out the p, and I get p times q is the variance of one Bernoulli random variable. So here x is Bernoulli. And then if I realize that a binomial experiment is just the sum of n independent Bernoulli trials, then I would be adding e of x binomial equals the sum of n of these, each of which has a mean of p. So doesn't that make sense that I would have n of them, each of them with a mean of p? So I would be adding p plus p plus p plus p plus p however many times, n times. And therefore variance of x binomial is equal to n times p times q, because each Bernoulli random variable has variance pq. So if I have n of them independent from one another, then their variance would be n times p times q. Are you with me? That's where these formulas come from. I did not just want to throw them at you and say, just take my word for it. What does that even mean, right? So I wanted to show you where those would come from. Of course, the formal proof is quite cumbersome. This is just a short way of looking at it, okay? So this is the mean of a binomial, and this is the variance of a binomial. It's just a sum of n independent Bernoulli, and we proved it for Bernoulli's. Get it? All right, so those formulas can be found on the top of page 8. So of course, if I wanted sigma for a binomial, this would just be the square root of npq. Right? It's a square root of the variance. I need to label these pages, so give me one moment. This was 5. This was 6. If you look on page 9, I gave you an example to try at home, and I also gave you all the answers. So when you get out of class today, you want to try those and make sure that you can do it on the calculator, of course. You're not going to waste your time going NCR, P to the R, Q to the N minus R. Do it on the calculator and make sure you get those answers that I provided on the bottom of page 9. I want to do page 10 right now. So let's say here, please do page 9 and check answers. This is page 10 of your notes. It is reasonable to assume that a health worker exposed to a certain virus has a 25% chance of developing the disease. So probability of developing the disease is equal to 1/4, 0.25. Let the random variable x denote the number of workers from a possible sample of 5 workers. N equals 5. 5 trials. Every worker is an independent trial. Let x denote the number of workers from a possible 5 who develop the disease. Why would the binomial distribution be appropriate? That's the first question. Why binomial? So whenever you are asked why binomial, your answer always needs to be because there are n independent Bernoulli trials. And here we have 5 independent healthcare workers, where each worker either develops the disease or does not develop the disease. So I have 5 independent Bernoulli trials where every person either develops the disease or doesn't develop the disease, and I have 5 of these people. So it would make sense that this is a binomial experiment, right? A binomial experiment is defined to be an experiment with n independent Bernoulli trials. Bernoulli meaning success or failure on each trial. Get it, right? So it's appropriate. Binomial is appropriate. Part B says, list all the possible values for x along with their probabilities. So this would be xi, p of xi. We'll do a few of them. So if I have 5 workers, there can be none who develop the disease, or 1, or 2, or 3, or 4, or 5. So it's important to realize that there could be 0 of them developing the disease also. And they're asking us to find each of these probabilities. So let's do 1 or 2. Why not? Let's do the first one. This would be 5, choose 0, 1/4 to the 0, 3/4 to the 5th power, meaning probability of developing the disease to the 0 power, because nobody does, and not developing the disease to the 5th power, because 5 of them do not develop the disease, if exactly 0 of them do. So this 5 choose 0 is 1. 1/4 to the 0 is also 1. So your answer is just 0.75 raised to the 5th power. So this would be 0.2373. Agree? How about the fourth one? This one would be 5, choose 4. 1/4 to the 4. 3/4 to the 1. So if I did not want to do this by hand, I would hit second distribution, binomial PDF of n, which is 5, p, which is 1/4, 0.25, comma r, which is 4. And I get 0.0146. All of these probabilities need to add up to 1. Do you get that? Any question? Can I please repeat what? Oh, of course. So each one of these is binomial PDF of n and p and r, where r ranges from 0 through 5. P is 1/4, n is 5, and r changes. Part C. What are the parameters n and p for this distribution? That's a simple one. They just want you to say that x is binomial np, where n is 5 and p is 1/4. Part D. What is the expected number of health workers who will develop this disease? All I'm going to do is say E of x equals n times p. I'm not going to do sigma xi p of xi, because all that would just yield n times p in the end, right? So just go n times p. I have 5 workers. The probability of developing the disease is 1/4. So when I clean this up, I get 5/4, which is 1.25. Of course, there is no such thing as 1/4 of a healthcare worker, so you're going to say roughly 1 guy will develop the disease. I only have 5 workers.
Round up.
You would not round up, you would round down to 1.
What is that with 1.5?
1.5, then I would say 2. E, find the standard deviation, the typical deviation from the mean for this random variable. So it's just a plug-in. Sigma equals radical n times p times q. So I get radical 5 times 1/4 times 3/4. This is instead of doing e of x squared minus mu squared and then taking the square root. You wouldn't bother with all that because you have shorter formulas now that you know that it's binomial. So radical npq. So this is radical. 5 times 3 is 15 over 16. F. In how many ways can we order the 5 healthcare workers? Order is important, so you're going to say 5p5, which is 5 factorial over 0 factorial. The formula for NPR is n factorial over n minus r factorial. So I get 5 times 4 times 3 times 2 times 1. So 120. G. Regardless of order, how many ways can you choose? Let's change that word 1 to 3. Regardless of order, how many ways can you choose 3 out of these 5 workers? I'm changing that word 1 to 3. So the answer to that is, how many ways can you choose 3 out of 5? The answer is 5, choose 3, because it said order not important. So this would be 5 factorial over 3 factorial 2 factorial, which is just 10. Because I get 5, 4, 3 factorial over 3 factorial 2, 1. The 3's drop, and I get 10. 20 over 2, which is 10. And H. I'm now on page 11. Find the probability that exactly 2 of these 5 workers develops the disease. That would be probability of 2. R equals 2. So this would be NCR, P to the R, Q to the N minus R. Plugging in, I get 5 choose 2. 1/4 to the 2, 3/4 to the 3rd power. Or if I'm too lazy to do this, I would do binomial PDF of n is 5, p is 1/4, r is 2. Does that make sense? All I did was binomial PDF and PR. Part I, what is the probability that none contracts the disease? I believe we already found that number. This is the probability that nobody contracts the disease. And that number was already found in the table, 0.2373. It was obtained by going binomial PDF of 5, n is 5, p is a quarter, and r is 0. We actually did it by hand. 0.2373. We have that value right here. So I'm just copying it from the table. Part J. Part J says, what is the probability that more than 2 contract the disease? Probability R greater than 2, more than 2. More than 2 does not include 2, right? I have to be careful with the greater than or equal to in this case because this is a discrete distribution. It's not continuous where it doesn't matter. So probability R greater than 2 is probability R greater than or equal to 3, meaning 3 or 4 or 5. So I could either find 3 products, which I don't want to do, or I could let the calculator do the work. This would be 1 minus probability of 0 or 1 or 2. After all, I want 3, 4, and 5 added together, so I'm going to take away all the rest, 0, 1, and 2, taken away from 100% or 1, because that's the sum of all the probabilities is 100%. You're with me, right? So 1 minus binomial CDF of NP2. N, of course, is 5, and P is a quarter. And R is 2. Let's do it. Let's find a proper answer for this one. So 1 minus second distribution binomial CDF of 5, comma, 0.25, comma, 2. And I get 0.8965. So 1 minus 0.8965 gives me 0.1035. That's the answer to part J. Do you agree with that? Yes? Okay, part K. What is the probability that no more than 1 contracts the disease? Not more than 1. That means probability R less than or equal to 1, right? Not more than 1, but 1 or none is what it's asking for. So this would just be binomial CDF of NP1. So 5, comma, 1/4, comma, 1. Because this is going to add probability of 0 plus probability of 1 up. It will do that work. Let's check this. We'll do it by hand and we'll check it also. So we have the number already for P of 0. I don't mind doing it again. 5 choose 0, 1/4 to the 0, 3/4 to the 5, plus 5 choose 1, 1/4 to the 1, 3/4 to the 4. Let's find this answer by hand and then let's compare to binomial CDF to make sure that we still know what we're doing. So this answer was 0.75 raised to the 5th, which was 0.2373 plus 5 choose 1 is 5 times 0.25 times 0.75 raised to the 4th power, I get 0.3955. So when I add these both, up, I get 0.6328. I want to make sure my calculator gives me that. So second distribution, binomial CDF of 5, 0.25, 1 gives me 0.6328 also. So it's good. And lastly, part L. If you actually observe all of the 5 workers developing the disease, would you reconsider your original constant probability assumption of P equals 1/4? If you actually observe all of the 5 workers developing the disease, so what's probability of 5 according to our binomial distribution? This would be 5 choose 5, n choose r, so 5 choose 5, p to the 5th power, 1/4 to the 5th, 3/4 to the 0. That's what I expect based on this model, right? So 5 choose 5 is 1, 3/4 to the 0 is also 1, so my answer is just 1/4 raised to the 5th, which is what? 0.00098. It's minuscule, right? It's practically 0, this probability. So according to this binomial model, the probability of 5 successes is supposed to be very small. So if I observe all 5 developing the disease, this contradicts probability of 5 equals 0.00098. Agree? So reconsider that P equals 1/4, meaning something's wrong with the model, because in reality, if you observe all 5 developing the disease, that doesn't match with what is expected according to this model. Which brings me to the final statement for today, which is this. Our successes are considered unusual if the probability, unusually high, let's say, unusually high if the probability of x greater than or equal to r is less than or equal to 0.05. Let me explain. You have some distribution, right? It's a discrete distribution, so I'm not drawing a continuous curve, right? And let's say I'm talking about some number of successes R, let's say. I'm trying to say that I would consider R to be an unusually high number of successes if the probability of R successes or more than R successes, which would be this and the next one, if this area were less than or equal to 0.05. Meaning, if R were already in the tail of the distribution, then R would be considered unusually high. Meaning the probability of being even worse than R or worse, it's like p-value, right? Probability of R or more, if that probability were very small, then R would be considered unusually high. Same thing on the left side. R successes are considered unusually low if probability x less than or equal to R is less than or equal to 0.05. So now I'm on the left side. of the distribution. Let's say this is R. So I'm saying consider this probability of this or fewer. And if this area is less than or equal to 0.05, then it means that R is in the tail of the distribution already. I'm talking about p-value again, the probability of being more extreme on the left side. If that's very small, then R is unusually low. Do you understand what I'm saying? So I could have done this problem, part L, using this definition too. Would 5 people developing the disease be considered unusually high? Is the question in L, right? So in part L, it's saying, is R equals 5 unusually high? So the answer is, let us consider P of 5 or more. But there is no more, because 5 is the largest it gets. So P of 5 turns out to be 0.00098, which is in fact less than or equal to 0.05, according to the definition of unusually high. Therefore, 5 is considered too high. Get it? You want to look at the area in the tail past that number. So the probability of that number and more, or more, I should say. Any question? Okay, see you Monday, folks.